functions. What rational functions are, by definition, is it's a polynomial function being divided by another polynomial function. Let me say it this way, or let me show you this way. I'm going to, since it's a rational function, use the term r of x. What that would equal, why did I use an r?
Rational.
It's rational. Very good. It's a polynomial divided by another polynomial. So I'll do P for polynomial and then Q because it's a nice letter in the alphabet. That's what a rational function is. And that's what we're going to look at today. So our learning goals are we can describe and explain the end behavior of a rational function from its degree and leading coefficients. And we can also graph and describe key features of rational functions. That's the goal for today's learning, all right? With that, as always, there's the vocabulary here that we'll get as we go throughout the lesson. So, what have we done so far? We have been working with polynomials. Today we're going to start working on rationals. So notice here, what's happening in that equation? Division. We're going to be dividing by another polynomial. Now what this means is we're not going to be just dividing by a number. We're going to be dividing by a function. You will have x's in the denominator. So f and g are polynomial functions. Now they can be constants, but either way, g cannot be 0. Now why could g not be 0? I want you to think on this.
Because you can't divide by 0.
You can't divide by 0. And Chris, I like how you pointed at the poster. Poster says you cannot divide by 0. That's a math rule. That's one of the 3 math rules. You cannot divide by 0. So g, the denominator, let's say that, the denominator will not be able to equal 0. All right, so the graphs will have very different curves. I call them C curves. So if you want to write this down, I call them C curves. They're not all going to look like C's, but very often they do. So if you want to put that in, the graphs are going to look like C curves. Okay, so the domain. The domain of a rational function is all reals except for the x values when solving the denominator, because again, the denominator cannot equal 0. So those are going to be the only excluded values. Okay, there are going to be some things that we talk about called holes, vertical asymptotes, horizontal asymptotes, and the critical points, y-intercepts, and zeros. I'm going to show you these. That's a set for you when you do your homework later on. This is like a cheat sheet when you do your Delta Math that you can look at as you go through it. Rather than spending all the time here, I'm just going to work examples, and you'll learn through the example, but this is your cheat sheet to refer back to. It's kind of your reference guide. Okay? So with that, let's get started. Give you a chance to turn your page. With rational functions, you'll see two different types of breaks that are possible. There are 3 different types of breaks on a graph. The one you will not see is this middle one. This comes from a piecewise defined function. So just put here piecewise function. That is called a piecewise function. That's when we have what's called a jump discontinuity, where the graph picks up and jumps from one place to another. That cannot be created by a rational function. So it's not going to be a rational that gives you this look, but a rational will give you this. This is called an infinite discontinuity. Okay, what it means is that there's a vertical asymptote. So what I'm going to do is add your notes here, this vertical line to represent. That line right there is called a vertical asymptote that we will solve for all throughout today. A vertical asymptote. Now this is an easy name to remember, an infinite discontinuity, because if you look at the break, that red dashed line that I just added in, if you look at the break, the blue function is taking off and going where? Where is that arrow pointing? Up to what value? Infinity. And this other side is pointing down to negative infinity. Thus we call it a infinite discontinuity because the graph's going to infinities at the breaks. They won't always have one going up, one going down. They can both go up. You'll see me do my arms like this. They can both go up. They can both go down. But most often, as the graphs approach each other, one will go up and one will go down. That's what occurs most often. The other type of break you will see with rational is what's called removable. And that's kind of like when you just take one little piece out of the graph. We also call this a hole. So go above that spot, and I want you to put hole. So on your cheat sheet, if you go back a slide, you will see the vocabulary for a vertical asymptote and a hole. Those 2 breaks are created by rational functions. These two breaks or discontinuities are created by rational functions. What creates the middle break? What creates this one? A piecewise function. Maybe I should say created by a piecewise function. Okay? So today you're going to see a lot of the first and the third type of breaks. Am I good to move on? Enough time for you? Okay. So a vertical asymptote, I have a picture of it here. Vertical just means it's going up and down. It's when the graph is beginning to flatten out and approach an x value. So it starts to flatten out and vertically flatten out. And this shows you arrows here that's saying the y is going to positive infinity as x is going to this value a. That plus means from the right side. We would write this as a limit. So you'll see this on Delta Math written this way. But typically you write it this way, especially if you take calculus. After this, you're always going to write this as a limit. This right here represents a limit. As x approaches a plus. Now you might be going, what does that a plus mean? That means as it's approaching a from the right side of the graph. As we approach that, the graph goes up. That's how you would represent this as a limit. And you could do the same all the way across. Okay, I'm not going to, but that's how you would translate that into a limit, especially moving forward in calculus. And since that's what I'm preparing you for, I'm going to write it as limits. I'm not going to take the shorthand way like this. Okay, so that's a vertical asymptote, and you can also have horizontal asymptotes. A horizontal asymptote will look like this. The graph is flattening out and approaching a value that's constant that's flat like this, horizontal, and so it's approaching the value b. Now how this would be written as a limit, as you would say the limit of f of x as x, on this case, goes to the right to positive infinity. You would say the y value that it's approaching is the value b. The only difference on the second one is you would have x approaching negative infinity because you're going left. Now you heard me say this last class, but I'm going to say it again because we got 4 new students today. When you write limits, there's only 3 options for y. Okay? As you go left or right, there's only 3 options for y. Y can rise off the screen, it can fall, or in the case you see up here, what's happening to this first graph? Is it appearing to rise forever, fall forever, or is it starting to get flat? Flat. It's approaching a constant. And the constant in this case is this letter b. Okay? Now over here, if you follow the graph from the right to the left, it's increasing, now it's decreasing, but what's it starting to do as you go further and further to the left? It's flattening out. So if I ask you, hey, what's this graph doing? Is it rising? Is it falling? Or is it flattening out to a constant? That's what you'd say, it's flattening out to a constant. Okay? So that's that's a horizontal asymptote. With that, let's get started. The first graph we're going to look at is 1 over x. This is called the parent function. It means there's no transformation. It's the most basic. Go to your graph, add an x-axis and a y-axis here. What this graph will resemble is a C-curve, meaning it'll come through like this, and it'll wrap around, and it'll follow the x-axis. You can add your arrows, just like that. And because this x power, what's the power of my denominator here? It doesn't show me a number.
1.
It's a 1. That's an odd power. Because it's odd, the other piece would reflect across the origin. Because it's positive, the first piece is in the first quadrant. If it was negative, it would be in the fourth. And because the x power in the denominator is odd, it reflects across the origin. That's what the graph would look like. So there's your sketch. Now let's talk about domain. Does this graph, let me back up. Domain, x values, y values. X. So show me an x-axis with your arm. What two directions does your x-axis point? Left and right. How far to the left does this graph travel? Negative infinity. How far to the right does it travel? Positive. So you'd think it's all reals, but it's not. There's a break. What x location breaks this graph?
0.
0. I'm now going to add that vertical asymptote. That's going to be right here. The parent function has a vertical asymptote at x equals 0. That's what that vertical asymptote is at. It's at 0. So here's what our domain would look like. We would say it goes from the left all the way up till this value 0. So from the left, that's negative infinity. And it continues on. This piece of graph continues until what x value? 0. Now, do we actually get to this asymptote?
No.
No. We approach it, which means it's a limit. We're getting closer and closer to it, but we never get there. For that reason, it's not a bracket, it's a parenthesis. Another way of thinking about it is this has an arrow. Anytime you're writing domain or range and you have an arrow, don't use a bracket, use a parenthesis. Because the arrow means you're going there, but you never actually get there. Remember, a limit doesn't tell you where a graph is, it tells you where it's going. An arrow doesn't tell you where the graph is, an arrow tells you where the graph is going. Okay, that's what an arrow tells you. So it's the same idea, parentheses. Now there's a second piece of graph. So we're going to use a union. Now let's talk about the second piece of graph. How far right will the second piece of graph go to? Infinity. Well, how far left does this second piece go? 0. Again, it has an arrow, so regardless, it cannot be a bracket. So it's 0 to infinity. Now let's go on to range. What's the difference between domain and range?
Range is y.
Range is talking about the y's. So go always from the smallest number to the largest, so bottom to top. How low does this graph go? Negative infinity. That's how low it goes. Now, how high does this first piece go? 0. Again, there's a break here. We don't call it a vertical asymptote. What will we call this one? A horizontal asymptote. The equation for this horizontal asymptote is y equals 0. So once again, just like the domain, the range would go from negative infinity until 0. We have an arrow. Does that mean bracket or parentheses? Parentheses. Anytime it's an arrow, that means you're not actually there. Parentheses. Union. This piece, how low does this second piece travel? 0. How high? 0 to infinity. Good. Okay, another way of translating this is like so. You could say the domain is all reals except for, what's the only value we did not include? 0. You could have said it that way. X does not equal 0. This implies all reals except 0. That's kind of what you're saying there. You would, if you were writing this way, you would need to write the x does not equal first. So you'd say x does not equal 0, comma, x is all reals. That means all reals except for 0. Now, I won't write this way because Delta Math does not have that symbol in it. So you'll have to write them like this or with inequalities. So they don't have that symbol there. What about the range? What is this saying the range is? Translate this from math to English. All real numbers except 0, but this time it's y. So y does not equal 0, comma, y-e-r. That means all reals except for 0. Okay, tell me about the graph. This first piece, is it increasing or decreasing? It decreased. What about this one? Decrease. It does not increase at all. This particular graph does not increase. The parent function does not increase anyway. What about decreasing?
0 to negative
We go off x values.
infinity.
So from left to right, what's this piece doing? It's decreasing, and this one? And they're both decreasing. What's that word that if the whole graph is decreasing? Do you remember what that word was? It started with an S. This is strictly decreasing. Strictly means it's only decreasing. And it would be strictly decreasing on the domain. Sorry, I'm pointing at the wrong thing. And the whole domain. So it's strictly decreasing from negative infinity to 0 and 0 to infinity. That's all it's doing is decreasing. Would we call this an even or odd function if it has symmetry across the origin? This is an odd function. Okay, a hole. We don't know what those are yet. Just put NA. This has no holes. Do we have a vertical asymptote?
Yes.
Yes. What's the equation for it?
2.
X equals 0. It throws people off because you think of it being up and down like the y-axis, but the y's on this line are always changing. The x's never do. The x stays at a 0. No matter where you are on the line, the y will change, but the x doesn't. That's why we say it's x equals 0. What about the horizontal asymptote?
Y equals 0.
That's y equals 0. Oops, forgot the colon there. Y equals 0. Do we cross the y-axis?
No.
No. Does this have any zeros?
No.
You got it. A lot of details there. That's the parent function. So the rest of the day, we're going to just look at some transformations from that. Do I have end behavior, though, when I go to the next slide? Nope.
X is
Okay. First, your packets. You have a 1 in your numerator. I meant to put an X. I remembered on part C. Put an X in your numerator. Instead of 1 over. Yeah, go ahead. Make it X over. All right. Now that you change your packets accordingly, question for you. Can I simplify mathematically and say this? Cancel, cancel.
yeah.
It's just 1 over negative 1 or 0 over negative 1. Would that work?
No.
Let's think about it. Let's plug in some numbers and see. Someone pick an X value. What's your favorite number?
5.
I hear 5. Giovanni was quick on it. What if it was a 5? If I did 5 over 5 minus 1, what would that mathematically equal if you simplified?
5 equals 5 divided by 4.
5 divided by 4. Okay, if I cancel. And let's just say I thought that was a 1. Is 1 divided by negative 1 the same thing as 5 divided by 4?
No.
No. What about if I thought it was a 0? Is 0 divided by negative 1 the same thing as 5/4? No. So that doesn't work. You can't cancel like that. You'll learn that's called canceling terms. You're not allowed to cancel terms. You're allowed to cancel factors. What are you allowed to cancel? Factors. What a factor is something that's multiplying. The reason you can cancel factors is because factors multiply. And what we're doing here is called dividing. What's the opposite of division? Multiplication. Right now, you'd be canceling something that's being subtracted. It's not opposites. It doesn't work that way. So anyways, nothing cancels here. So what happens? First, for your domain is established off the denominator. What are you not allowed to divide by? 0. So if you want to solve for your domain, you take the denominator and say that cannot equal 0. And you solve from there.
1.
So if x x minus 1 cannot equal 0, what does that mean x cannot equal when you solve? X cannot equal positive 1. Very good. In terms of parentheses, that would mean this. The graph is going to go from negative infinity all the way, instead of 0 this time, it's going to be a 1. Union 1 to infinity. So we're just changing our values from last problem. Again, I would need to say XER here. It's all reals except for 1. So go to your graph and add a vertical asymptote, approximately right 1 unit. So go right 1 unit and add a vertical asymptote. Here's your x-axis. Here's your y-axis. This is x equals 1. Go to vertical asymptote and go ahead and put that in. X equals 1. Now we got that in the domain from where? Denominator. Okay, the range. We'll get to the range in a second. We'll do increasing, decreasing, even, odd, and all in a second. I'm going to skip down to the y-intercept. To find a y-intercept, you substitute a 0 in anywhere you see an x. So the y-intercept would be located when you have 0 over 0 minus 1. Erase this. 0 over 0 minus 1. That's what you do. You plug in a 0 for any x. So what I'm trying to find, let me say it this way. I'm finding f of 0. That's how you find a y-intercept. You plug in 0 anywhere you see an x. So what is 0 minus 1? Negative 1. And what is 0 divided by negative 1? 0 divided by negative 1 is 0. So that means the y-intercept is at the origin. it. So we have a y-intercept at the origin. That's because we plugged in a 0 everywhere you saw an x. A 0 is found by setting the numerator equal to 0. Only the numerator. Well, that's already solved for us. So where do we have a 0? At 0. Well, we already have that point on there. Cool there? The rule for the horizontal asymptotes is you divide the numerator by the denominator. And specifically, you can do a shorthand of looking at just the leading term and leading term. What it will be y equals, what's x divided by x? So I'm simplifying. I'm not looking at the negative 1. I'm just taking the leading terms. What's x divided by x? Those would cancel because they're identical. No matter what numbers they are, those would cancel and it becomes 1. So now go to your graph and add a horizontal asymptote at positive 1. Like that. That's y equals 1. Now there's some rules on the cheat sheet and it says look at the powers. So I'm going to let you add that and I'm going to explain to you the cheat sheet. So on that slide I skipped, it says if you look at the degree, what's the degree of the numerator? 1. What's the degree of the denominator? 1. There are 3 rules. There's 3 possibilities. Either the degree is bigger in the top, meaning bigger in the numerator. The degree is bigger, option 2. Degree is bigger in the denominator, bigger in the bottom. Or the degree is the same. Which is the case here? Am I bigger in the top, bigger in the bottom, or the exponent is the same? So the rules are BOBO, which stands for bigger on bottom, y equals 0. Bottom, bigger on top, there's no horizontal asymptote. Or eats DC, exponents are the same, divide coefficients. Exponents are the same, so you would divide the coefficients. I have 1 there, 1 there. What's 1 divided by 1? 1. Pointing on the slide, the green one. It's y equals 1. That's where you get that from. So, how do I get the rest of my graph from here? This graph is supposed to look like a C-curve. What's my power in the denominator? Even or odd? Odd. So on our new origin, called the new origin where the asymptotes cross, we should have C-curves. The point I have is here. So the way the graph would have to look is this piece would have to curve this way. This is doing this without a calculator. This is how you graph this without a calculator, which you are responsible for on the test. I'll have you know. So I have this piece. Because this is an odd power, the other piece would reflect this way. Like that. And so that's how this graph would look. Now, I want you to say that this is still neither even nor odd. And I'm going to explain this. When this says even or odd function, what we're talking about is does it reflect perfectly across the origin? When you look at the true origin, does this graph reflect across the origin? No, and it doesn't reflect across y, so that's why it's neither even or odd. However, for graphing it, because your power in the denominator was odd, it will reflect oddly across the asymptotes. If that makes sense. So if that was a 2 in the denominator, what would be different? You don't know. Let me just show you. Really quickly, I'm going to go to the calculator. Let's play around for a second. Open up your calculator. Go to new document, don't save. Let's explore for a second. There's the back there. Press Control Divide to get a division. I'm going to put a 1 in the numerator and an x squared in the denominator. Like that. Hit enter. What do you notice about the C-curves this time? Are they reflecting across the origin? No, how are they reflecting instead? There you go. Now press tab. Press tab. Go up to change that equation. This time change this 1 Let's just make it an x plus 1. Don't just do it just an x, because that's going to do something new I haven't taught you yet. So do x plus 1. So it's not even. See how it's not directly even, meaning it's not a perfect reflection? But do you see how the pieces are going left and right rather than diagonal? That's kind of going to be your rules as you go forward. Okay. So you look at the denominator. What's that power? I'm going to change it to a 3 now. What do you think is going to happen with this being a 3? Does it go across diagonally? Yes. Now is it perfectly odd? No. And that's why if what was our problem we were actually working? It was x in the numerator. What was on the denominator? X plus 1?
X minus 1.
X minus 1. Okay, that's why this piece, it's not perfectly odd, like meaning over the origin, but you can see how it's rotating diagonally. So that's why you would say it's neither even or odd, but when you graph it, that's how you do it, is diagonal, because the denominator's power is a 1. How are we doing so far? All right, tell me about, now that we have it drawn, the range. Is it all reals? Does it go forever down, forever up? And never skip any values?
All reals except for 1.
All reals except for 1. For brevity, let's just write it that way. It's all reals except for 1. All reals except for that asymptote. The graph, is it increasing or decreasing here on the first piece? Decreasing, and here? Decreasing, so it doesn't increase. If it's always decreasing, what do we call that? Strictly, I got dyslexic, sorry, strictly decreasing on the domain. I'm just going to write on domain rather than writing all of that out. It's strictly decreasing on its domain. We still have no holes. We don't know what that is yet. Once they come back. Do you have a? Did you get a tardy pass? Perfect. And here's the sign up. All right. Ready for the next one? Part B. Now on part B, I want you to change that to an x again in the numerator. Go ahead on your part B. Put that x. Put the x in the numerator. Now I want to start preparing you for what you're going to see online in your homework. This is how Delta Math does it. So you should, let's go back to the graph and have this graphed in, and what we're going to do is write down a table. So go to your graph. Let's type this graph in, which I think I have it in here. And pull up the table. How do we pull up a table? Control T. Hit Control T. Now, when we're working with limits, sorry, let me pull back one more thing. What x value do you see all the way across here? 1. Each one of these is x value 1. We're going to look at 1, and when we're looking with limits, we're not going to leave the x values as they are. I'm going to change it and make it count by 10,000ths. So do this. Press Menu, Table, Edit Table Settings. Menu, Table, Edit Table Settings. When we work at limits, I need to start at 1. Why am I starting at 1 again? That's the x I want. When we work on limits, I wanted to count by 10,000. So do 0.0001. I'm going to do 4 digits here. And then press OK. Now, this is the values that I'm going to use to solve to get my answers here. So I'm going to copy this over. Now that I have it over here, we're going to get our values. So let me explain what's going on. Now, the limits, when you see them with the little minus and the little plus, that means, remember, a limit, it doesn't tell you where the graph is. What does it tell you? Where it's going. This table is telling you where the graph is. what we're going to do is we're predicting where is the graph going as you approach 1 from, if it has a little minus, that means from the smaller numbers. So as I approach 1 here, you see how these are getting closer and closer to 1? If you look this way, what does it appear that the y values are approaching? Are they approaching a number, or are they just going to negative infinity? They're decreasing without bound quickly. You see how that's almost negative 5,000? That's almost negative 10,000. You see how it's going down really fast? That means this is decreasing without bound. So put, it's falling, negative infinity. Well, worked for a moment. There we go. Now, when it says 1 plus, what's the difference with 1 plus? That means we're looking what's happening as the graph from numbers that are bigger than 1, as we approach 1, what's happening. And again, do not leave your numbers as like your table as 0, 1, 2, 3, 4, like that. It's too big. You won't be able to get the right answers all the time. As you look this way, what does it appear is happening to the y's as your x get closer and closer to 1? They are increasing without bound. So you do a positive infinity. Make sense so far? The third value only exists. Here's the rule. The limit at 1 only exists if these two are the same values. Are these the same values or are they different? So you would say this does not exist. I'm not going to do an equals. I'm just going to say does not exist with an arrow. Now, f negative 1, a limit tells you where the graph is going. F negative 1 tells you where is the graph actually. You would actually look at 1. What value is that? Again, don't put equals because technically it doesn't equal undefined. It is undefined. F negative 1 is undefined. You're going to have a lot of problems on your homework where you have to do this. The way it's going to be different on Delta Math is they're going to give you a little table and you'll type in the values. So there's 3 numbers you need to type in to figure this out. You would need to type in 1.9999 and 1.0001. Just remember, a limit doesn't tell you where the graph is at. It tells you where it's going. And you would just need to use some intuitiveness to know it's not going to negative 9999. That's going to negative infinity. That's just decreasing without bound. That's going down fast. And the opposite is true for 1.2001. Okay? So that's how you would write those limits. So here's the question. Is it continuous? It's based off of this. Were these the same?
No.
Okay, because these are the same and it was different than F91, it's not continuous. That's the rule. If they were all the same, it'd be continuous. But since these are not all the same, this is not continuous. This is what it's using the continuity test. This is not continuous. Since, well, there's a lot of reasons. Since the limit of f of x as x approaches 1 minus does not equal the limit of f of x as x approaches 1 plus. That alone right there, because these two were not equal, means it's not continuous. But just to add one more rule, and that does not equal f of negative or f of 1 either. Because they do not equal each other, it is not continuous. For it to be continuous, these two limits would have to be the same. And if these two limits were the same, by definition, this would be the same. And not only that, it would have to equal the function at that value as well. But since they all are, none of them are equal to each other, this is not continuous. Yep. If just one of them is not equal, they are not continuous. So, what would it look like for it to be continuous on your homework? Every answer needs to be the same. What's it need to look like to be not continuous? Just one answer is all it takes. As long as one's different, it's not continuous. It just one is different. Does that make sense? Okay. Describe the end behavior. So now we're going to do the end behavior. So let's I'm going to just take a picture of graph. Actually, I'll do the picture from here. So I'm going to hit Control T, and we're going to do our in behavior. Tools, screen capture. Okay. So in behavior, this means we write the limits. What's happening to the graph? In behavior means as you go forever to the left and forever to the right. As you go to the left without bound and to the right without bound. We want to write what is happening to our graph. Okay, so we're going to write two limits here for our in behavior. So I'm going to write first the limit as we go to the left. So in behavior wants to know what's happening as you go to the left and what's happening as you go to the right. Translate negative in x approaching negative infinity. Translation, that's x going left. X approaching positive infinity. Translation, x moving to the right. What is happening to this graph as we go left? Remember, there's three options. Is the graph increasing without bound? Is it decreasing without bound? Or is it flattening out? It's flattening out. Now, if it's flattening out, what value is it flattening out on? What's the y value? 1. It would be 1 here. 1. Okay, what about the right? As we go right, does this graph rise? Does it fall? Or does it appear to be flattening out? It's flattening out. What y value is it flattening out on? 1. Now the reason it said use your vertical horizontal asymptotes, really all it should have said is use your horizontal asymptote. That horizontal asymptote right there was y equals 1, and that's where we got those numbers from. So really, we didn't have to use its vertical asymptote. We just need to use the horizontal asymptote singular. That's all we needed to use to find its in behavior. All right, now we're just going to replicate that over and over. I'm just going to make the functions more difficult as we go. We could use calculator, but I'm going to use some just good old-fashioned algebra for to review you on some stuff before we forget the algebra. So I want to do that first, and then we'll check with the calculator. All right, let's check the next problem. We have this problem. It says, for each of the following, find and analyze all the key features. So here's the order I would go in if I was using algebra. First, I would find the domain. The rule for domain is you assume it's all reals unless you see either division, square root, or log. Do you see any of those in this function? Yeah, what do you see? Division. What are you not allowed to divide by? Okay, so that cannot equal 0 down there. We need to factor that. What's a method that we've learned to factor a trinomial? Stay with me, Jonathan. How about the x method? First, you have to look for a GCF. Is there anything in common there? No GCF. Secondly, you would do an x. We're looking for factors of a times c that add it to b, where this is a, b, and c. What is 1 times negative 6? Put that at the top of your x. And b is negative 1. What are factors of negative 6 that add up to negative 1? Negative 3 and positive 2. 2 times 3 is 6. But if you make it a negative 3, 2 minus 3 is negative 1. Okay, those are our factors. You split this term's power. And so what we found out is this denominator could be rewritten as, if you split this as from a square to just an x times another x. We plug in those numbers and we can rewrite the denominator like this. Now why would I write it like this in what's called factored form? Because from here we can find out what x cannot equal. What would give me a 0 in this factor?
Negative 3. X minus 3.
If x was a negative 3, then it'd be negative 3 minus 3 more. That's negative 6. That doesn't work. What x value would give me a 0 there? Positive 3. So x cannot equal 3 according to zero product property. If that's a 3, I'm multiplying by a 0. I'm going to have 0. So x cannot equal 3. X cannot equal 3. What else could x not equal?
Negative 2.
Negative 2, good, because that's what you're looking at, is where those, so it could not equal 3, it could not equal negative 2. Other than that, x could be all real. So it's all reals except for those values. Now, I'm going to do the same thing with the numerator. We could do a next method. You might recognize that as a difference of squares. There's a shortcut for that. This is A. This is C. I'm missing which letter? But B is 0x if you want to use X method. So 0 would go there. Get my colors right here. 0 would go here. What is 1 times negative 4? What are factors of negative 4 that add to 0? What are the factors of 4?
Negative 2 and 2.
There's 2 and 2, and there's 1 and 4. It's got to be a 2 and a 2 to get to 0. How do I make it be 0?
Negative 2.
There we go. And so this would factor as x plus 2 and x minus 2. Now, why do I write that? Because I'm going to have a hole. This is the first time you see a hole. A hole occurs when a factor cancels. You see how I could cancel that factor? What x value was it that I just canceled there?
2.
This is a hole at, I'm going to do the at symbol, at x equals negative 2. So what would the hole's location be? It would be negative 2, comma. Now to get the y, you plug it into what's left over. So if I plug in a negative 2 there, it's negative 2 minus 2 more divided by negative 2 minus 3. When we simplify that, we'll have the actual point.
Wait.
Okay, so I don't want to go too fast here. Why do we know the hole's at negative 2? Yeah, we call this a removable discontinuity earlier because you remove it from the problem. That's why it's called removable. You remove it from the problem. So we know it's at negative 2. So what you do is you plug in the negative 2 to the remaining equation to find out what the y value is. And so now I'll simplify and we'll have our final point. What is negative 2 minus 2 more? It's not 0. Negative 2 minus 2 more? Negative 4. And what's negative 2 minus 3 more? Negative 5. What's negative 4 divided by negative 5? Can I just make it positive? Yeah, let's just make it positive 4/5. Or you could do it as 0.8. That would be the hole right there. Now a vertical asymptote is any factor in the denominator that remains. Do I have any factors on the denominator that remained? Yeah, what's its x value? 3. So put x equals 3.
How'd you get the vertical asymptote?
It's any factor in the denominator that remains. Yeah, so you see how we have an x minus 3 here?
Yeah.
So that 0 would be 3. That's where the graph would be undefined. So here in a second, we'll draw this thing. Horizontal asymptotes. Okay, so I'm going to go off the rules of the exponents. Is this a situation where the exponents are the same? Is it bigger on top or is it bigger on bottom? They're the same. So since the exponents are the same, I'll go ahead and put that rule. Exponents are the same. Divide your coefficients. It's going to be y equals 1 divided by 1. What's 1 divided by 1? 1. We're going to have a horizontal asymptote at 1. The y-intercept occurs anytime you plug in 0. I'm going to use the simplified version. It'll be easier. So it'd be 0 minus 2 over 0 minus 3. Negative 2 divided by negative 3 is 2/3. And finally, a 0 occurs when the numerator equals 0. Using the simplified version, when would this equal 0? At 2. So now let's graph this without a calculator. Add yourself an x-axis and a y-axis. I'm going to do the vertical asymptote first. The vertical asymptote occurs at 3. So I'm going to just assume this is about 3 right here. And the y-intercept is at 1. So this is at, not y-intercept, I'm sorry, horizontal asymptote is at 1. The vertical asymptote is at 3. I have a 0 at 2. So on the x-axis right there at 2, I should have a value. We're going to have a hole at negative 2 4/5. What that will look like is an open circle at negative 2. Now 4/5, is that bigger than 1 or less than 1? Less than. Just do an open circle there. So I did a 0 at 2. The y-intercept, I didn't do that. That's 2/3. That would be right there. So now I connect my graph. So it goes like this.
Where'd you get the open?
That's the hole. Yep, it goes like this. And now for the other piece, look at the simplified version. On the simplified version, is my denominator even or odd? The denominator.
Odd?
Odd. The denominator is odd. It's a first power, which means it'll be over here. The simplified version is what you go off, not the original unsimplified. So that's what the graph should look like. Fun stuff, isn't it? Okay, what happens as we go, what direction is this saying? Left. What happens as you go left? Does this graph rise, fall, or get flat? Flat. What value does it get flat with?
0.
1. It gets constant, it approaches the constant value 1. What happens as we go, what direction is that?
Right.
Right. What happens as we go right? Up, if rise, fall, or does it get flat? Flat. What's the constant value it gets flat with? 1. Okay. You might notice I threw in 4 more limits. Now, why did I do that? I did it for the other discontinuities. Let's do 3 first. The vertical asymptote. Do 3 with the minus, 3 with the plus. The minus and the plus graphically means you look just what's happening just to the left of 3 and what's happening just to the right of 3. Just to the left of 3. This piece that's on the left side of 3. What's that piece doing as it gets closer to 3? Is it rising, falling, or flat?
Flat.
No, don't say flat. That's like constant this way. It means horizontal. When I say flat, I mean horizontal. Is this rising, falling, or horizontal flat? It's falling. What symbol means falling? Negative infinity. Now the 3 plus, that means the piece that's just to the right. As you approach 3 from the numbers greater than 3. As you come towards 3 from numbers that are bigger than 3. That's what it's saying. As you come from the right, what's happening? Is it rising, falling, or is it getting flat, horizontal? Rising. So it would be positive infinity. Now what's our only other discontinuity in this graph? Not 2, but negative 2. So put negative 2 with the minus and negative 2 with the plus. Now this one, if you come to a point like this, this is the easiest of all of them. If you are approaching this point like that, you're just going to put the y value of that point. What was the y value at that point? As I come to negative 2 from this side, and as I come this way, I'm approaching this y value. What's the y value? 4/5. It's kind of like the situation of it going flat. That's basically the situation. But it's 4/5. You just put that point in. So this last limit right here, you see how these are the same? Because those are the same, what would exist is you could just write limit as x approaches negative 2. You could do it without the plus and the minus because they were the same. What is it on both values? 4/5. Because these two are equal, because those two are equal, you could just write it as one limit if you desired. You don't have to write it as 2 limits. Yep. So there's a lot going on here. Let me ask you about the limit at 3. Could I write that as one limit? Just saying the limit as x approaches 3. No. Why can I not write it? Because these two are not equal to each other. Let's go ahead and just add that to the notes. That'd just be good to add. Because these two are not equal, the limit at 3 would not exist. Does not exist. because these two are not equal, the limit at 3 does not exist. But at -2 it does because they are equal to one another. It would not be continuous though, because f of -2 would not exist. So it still would not be continuous because f of -2 would not exist. It's a hold there. It's not an actual point.
What about the
At 2 it would exist, and at here at 0 it would exist. Is that what you're asking about?
yeah.
It's okay if it's a different question.
It's the remember the first limit, the 1 equals 1?
Yeah, so on this one, let me write it this way. To add to this, f of -2 would not exist, or would be undefined. F -2 is undefined because it's an open circle. It's undefined. F -2 is undefined, so it's not continuous. Here, f -3 is also undefined because it's an infinite discontinuity. Anytime it's a whole or, if it's a whole or a infinite discontinuity, it'll be undefined at that location. It'll still be undefined. The limits do exist because the limits don't ask where is it, it asks where is it going. And they're going to that spot. So the limit would exist, but the point itself does not exist. I put a -3 here. Someone correct me, I shouldn't have put a -3 there. What should I have put there?
Positive.
+3. There we go, let's correct those notes. So I didn't have much to teach you today, did I? Hardly anything new at all?
What do you mean hardly?
Mostly review?
Yeah.
Mostly review?
It's still this was everything.
We're starting to move into some pre-cal. Hey, let's roll it up again. Let's do it again.
I mean, we didn't even know we were gonna do last
All right. All right, let's start back over. So, when we walk through this, what's our first step? Phones up, please. Phones up. What's our first step as we reload here? What have I been doing first each time?
Doing the bottom part.
Yeah, I look for the domain, and on this one we know that we cannot divide by 0, so that's where I'm going to start. I could say does not equal 0, but right now, if I say does not equal 0, I can't solve that yet. We need to do something with that. What do we need to do? Let's do an X method to factor this. We are looking for A, B, C here. Factors of, what's A times C?
25.
25 that add up to be 10. Numbers that multiply to be 25 that add to be 10. Do y'all know what they are?
5.
5 times 5. So what does that mean for our equation? We split this power and it becomes...
X plus 5 and X plus 5.
Okay, now since they're the same thing, do I need to write it twice?
No.
I could do a squared just like that. Now what about in the numerator? That's linear. I don't need to do an X method here. Is there any GCF?
No.
Nope. So it just stays as 5x plus 21. Okay, domain. This is anywhere, again, where the denominator would equal 0. So it cannot equal 0. So what x value would I get there?
-5.
-5. So x cannot equal -5, but what can x equal?
Any other number.
Any other number, all other reals. Are we good so far?
Yep.
Yeah, go ahead. So holes. Holes come from whenever you can cancel a factor. Can I cancel any factors?
No.
We have no holes, no removable discontinuities. Vertical asymptotes, as you notice, I've grouped those together. These come from any factor that's remaining. Do I have any factor that's denominator remaining? Yeah, I do, right here. What can x not equal? Okay, so notice your answers are backwards here because the vertical asymptote, it does equal it. Here the domain will not equal it. Instead of having a graph, we are going to have a vertical asymptote at -5. It happens twice, that doesn't matter. It's just going to be a vertical asymptote in its place. Horizontal asymptote, what you do is you look at the powers. Okay, what's true this time? Is my power bigger on the numerator or denominator. It doesn't matter if you look at the start or the finish, but I think it's easier this way. Bigger on bottom. So the rule is BOBO. If you want to write this down, the rule is BOBO. And what that stands for is bigger on bottom, y equals 0. Bigger on bottom, y equals 0. Now the intercept. Do y'all remember how to find the intercept?
fx is 0.
You put f of 0. Now that means every x becomes a 0. I think it's easier to use factored form. So it would be 5 times 0 plus 21 over
0 plus 5 squared.
0 plus 5 squared. Okay, let's simplify here. What's 5 times 0?
0.
0. I'm just going to cross that out. So it would be 21 over
25.
21 over 25. Does that reduce?
Yeah.
No, I don't think so. I think it's just going to be 21 over 25.
Yeah.
And then zeros. How do you get a 0? You set the numerator equal to 0.
Oh, yeah.
So let's do some mental math here to save time. So you would start with 5x equals negative 21. And then what would you do last?
Negative 5 divided by 5.
Divide by 5. And so what does x actually equal?
X is equal to negative 21 over 5.
Negative 21 over 5. That's from the numerator. That's where you get that. Let's see if that's enough information for us to graph this. I didn't check my graph last time. Should have. I feel. All right, Asif, how you doing? You doing all right? Okay. So we have a vertical asymptote. The vertical asymptote is left 5. 1, 2, 3, 4, 5. I'm going to say it's about right here. I'm going to say that's negative 5. X equals negative 5. 1, before, negative 3, negative 2, negative 1. Okay. We have a horizontal asymptote. Y equals 0. We have a 0. Negative 21 over 5. What is that as a decimal? Does anybody know? Negative 4.2. Good. Negative 4.2. So at negative 4.2, which is right in there, we're actually going to cross that axis. And we have a y-intercept at, yeah, which is, I think, 0.96. No? 0.84? I don't know where I was thinking. 0.84. So this would be below 1. If 1 was up there, I put that there. Okay, this I think is going to be a tricky graph. Here's what I think it's going to come up and then curve down. But I'm going to check it in the calculator just to make sure before so we don't have to erase. Let's go graph this one. You press tab up. Our equation was 5x plus 21 over, I'm going to make sure I didn't make any mistakes. Originally it was x squared plus 10x plus 25. Does it do what I said it would? Yep, does that.
What did you do with F?
I did the original. I did the original like that. And you know what? I'm just going to graph that in there like this. That's how I should have done it. Order send backward. Will this work? I'm going to keep trying this. I might have to do this too many times. Because I think if I do it all the way to the back, it's going to disappear. Well, it's taking too long. Okay, so it comes up. Whoops. I got crooked there. It comes up. And then it hit here, and it approaches this asymptote like that. And then what made it not go diagonal? Why did it not go diagonal this time? Tell me about the denominator power. It's even. So and this one came off this way. It wasn't as tight, so I'm going to do it like that. But that's how that graph looked. Okay, so what happens as we go left? What happens to this graph as we go left? It flattens out. It doesn't rise. It looks like right now it's rising, but it actually flattens out on this asymptote. And so what value is that it flattens out on? 0. Yep, it flattens out to 0. What happens as we go right? It flattens out on 0. Use your your horizontal asymptote for that. Okay, do we have any breaks? At -5. I'm going to do a -5 minus and a -5 plus. What's the difference in those two? One's from the left, one's from the right. What's happening on the left side of -5? The graph rising, falling, or horizontally flat? Falling. What's the symbol for falling? And what about from the right? It's falling. Now, okay, delta math threw me off here because delta math will say those are equal and it writes it as one limit. I don't think true mathematicians would say that. I need to check up on this. Because in negative infinities, even though they're both negative infinities, are those real numbers?
No.
No, you would say this does not exist. Now I might have to change that later, but I believe you say it does not exist since these are not real. Since negative infinity is not real. They're not equal to each other.
How would negative infinity not be real in that situation?
Because it's not a real number. Negative infinity just represents it's going down forever. But let's think about it this way. What if we were to plug in a number? Does this actually mean that they're falling at the same speed?
No.
No, one might be way lower speed-wise than the other, like if you compared the two. So that's why, since it's not a real number, you just say it does not exist. Now, delta math actually does do it. At least it looked like to me when I was looking at the examples. But I'm pretty sure that's a math error. So I want to be correct here. If you ever go to negative infinity, it's not going to exist at that number. Now, that's the only break, so we don't need this other limit. We don't need that. There's no other discontinuity. All right. Let's sneak in one more here. Let's try part C. You guide me through it. What do we do first?
The domain in the bottom.
I'm going to factor it so we can do the domain, holes, vertical asymptotes. All right, in the numerator, you could do X method if you like, but there's the easier method of factoring. This has a GCF. What's common? 2x. They both have a 2x. If I divide out 2x, what's left over in this first term? X. And if I divide this by 2x, there we go. I'm going to do an X method, though, for the numerator. Factors of -4 that add up to be -3. What are they? So it's not 2 and 2 this time. It's 4 and 1. Which one has to be negative? 4. I split the 8 terms power, so it becomes x minus 4 and x plus 1. All right, from the factored form, how do I get my domain?
7 is another.
Can't divide by 0, so what can x not equal? What if it's here?
It's 0.
You would say 2x does not equal 0, and then you would divide by 2. What is 0 divided by 2?
0.
Okay, so it can't equal 0, and what can it not equal right there? -2, good. What can x equal then?
All real numbers.
All other real numbers, good. Do we have any holes? You look, does anything cancel out? No holes. Do I have any vertical asymptotes? Yes, any factor left over, which we already solved here. At 0 and -2. Okay, horizontal asymptotes. I think it's much easier to look at the original. What's true about my powers this time? Are they bigger on the top, bigger on the bottom, or are they the same? They're the same. If your exponents are the same, It's eats DC. Divide your coefficients. Y equals, how many x squares do I have in the numerator? 1, and the denominator?
2.
So it's y equals 1/2. For a y-intercept, I'm going to plug in 0. I'm going to use the factored form. And rather than just plugging in a 0, what will this become when I plug a 0 in there? It'll be a -4 times 1 over 2 times 0 times 2.
Oh,
That's -4 divided by 0. Can I divide by 0? No. So this does not exist. You can't do that. So no y-intercept. It will not cross the y-axis. Zeros. How do you find zeros? Numerator equal to 0. Where are zeros going to be? -4?
positive.
+4 and
-1.
-1. All right. This time I'm just going to copy the picture over. So let's go to the calculator. All right, as quick as we can. What was the numerator?
X squared minus 3x
Minus 3x.
minus 4.
Minus 4. Denominator?
2x squared.
All right, here's our graph this time. You'll notice it looks
What the heck?
different. Yeah, we'll talk about that.
Oh,
There's 3 lines.
oh yeah.
Yeah. And when we pick back up, we'll cover this problem here.